Okay, so hello everyone. Thank you for coming to this session. I'll start it now in order that we don't get too late for lunch. So it's quite hard to do a session after the last one, but let's see if the math is fun enough, okay? So I'm going to talk about CRDTs and give a little bit of examples by connecting it with Redis. But the aim here is more to show what you can expect if you are used to work in a very sequential setting where you only lead with a single instance, and then you move into a setting that is multi-master, and you are doing things in multiple locations. So let's see which things are going to change, and what you can expect to be like reasonable. So as a motivation for why we need this kind of technology, I have an example here. I have tried to find an example that ties here to the United States. And I actually found a very interesting blog post about this, that you had one of the American presidents, he died on the mid-19th century, and the news of his death took a long time to travel the continent, okay? So it took almost 3 months to reach this region. So this tells us something about the speed of communication in the 19th century. And through that blog post, I found an interesting link to this concept, which I found it at least very interesting, called the Isochronic Map. So these were done by, I believe, an early statistician, Francis Galton. And that thing shows the travel time that you can expect when going from London, from the UK to other parts of Europe, so that is the green region. And then as you change colors, you are seeing more days. So 10 to 20 days, 20 to 30. So this was actually the latency of the world in the 19th century, okay? This is what you could expect. So now we can, I thought about starting from this map and giving some more recent numbers. So I did a small experiment with this site here. I don't know if it's very accurate or not, but you can see, I do it from where I live, from Portugal. You can see that, okay, if I'm connecting to a site which is quite nearby, I get under 4 milliseconds latency. So that's what you can expect if you are connecting to something like as an end user close to your network. Within Europe, you get 40, but then you start getting more. So although the communication speed is much faster than it was in the 19th century, there are still these big differences across the world. And things are not going to improve. Okay? So we are already very close to the limits of the speed of light. And actually, things are going to get worse. So I got another slide about delay-tolerant networks, a project from NASA, and also something from our European Space Agency. And you have there the one-time and round-time trip latency when you are communicating to Mars. So as we keep expanding, the problem will only increase. So I believe we live in a time where we are in the best conditions in terms of latency, and things will go worse again, okay? So we need to have systems that can operate into this kind of environment. So I try to, well, I will start using lots of Greek letters, so that's the funny part. So we have the small lambda and the big lambda. So you can think about the small lambda as a latency you can expect if you are right next to the machine or if it's very close to your network. But the moment you have to coordinate with another machine on the other side of the world, you get into the big lambda region, okay? And so if you only operated with a single instance, you are in the small lambda. If you go for something called, if you want strong consistency, and I must be fair, there are some problems that you can only solve if you have strong consistency, okay? But you should not use it for everything, blindly, okay? So you should know how to distinguish the problems that need it and the problems that can be done in a faster way. But then you have to pay a price of high latency. So you might have to pay a big lambda to 2 lambdas, depending on where the clients are and where how the replication quarantine is set up. If you go for something with less properties, like a primary backup solution, then you might have some data that is outdated and it's being like refreshed asynchronously. You might experience some smaller latencies. But what we'll care about here, and this is why CRDTs are used, is to be able to operate in a multi-master setting where you have the low latency point all the time, okay? And then data will be propagating on the background to other regions and being reconciled. So again, the best thing is if there was no price to pay, we would want strong consistency. But since the world is complex and partitions can happen and there are high latencies, there is a push to use this kind of technology. So when we use a single site or when we are using consensus, we keep the illusion that we are operating on a single replica. And this makes life very easy for the programmer because we see as if we are programming in memory. We do actions and there is a sequence of actions. So what I want to show here is that we can look at the actions that we did, and these actions form a total order. You know what was the last action that was done, what was the third from the last, and I think it's easy to understand that if you keep a log of all the operations, you can look at the log and see what is the current value. It's very easy, okay? It will depend on what you are doing. If you are writing to a register, typically it will be the last value. So we have this very organized setting, which is a total order. But for this, you need consensus protocols, you need synchronization. So we are going to relax this. And in this setting that I guess you are interested for Redis CRDTs, as an example, we are in an eventually consistent multi-master setting. So now things get a little more different. Now, we have a partial order of all the operations that are happening on the network. So you could think about it as a partially ordered log. And there's some other systems that try to implement something like that. So in a partial order, things get a little more complicated. You still have operations that are related to each other. So for instance, O and P occurred after O in the log. But you also have pairs of operations that are concurrent, that were submitted concurrently. And Iftachol talked a little bit about that in the keynote. So the idea is that we can still look at that. If we capture the partial order of what happened, we can explain what should be the value of the system. Okay? So that is the key idea. So if you kept this partial log, you could build any CRDT. So this is going to be the explanation of what you should expect when you do queries. You should be able to express the query in terms of looking at a partial log, and from that you see what are the values that you want to show to the user, depending on the data type. Of course, the real partial log is not present unless you stop issuing operations. So actually what you have in the many replicas is that you have a local vision of the partial log that is growing all the time. But each replica might have a different vision of that. So each replica will look at what it knows about the evolution of the system and give you an answer. So as a concrete example, what is counting? You have a counter that can be incremented and decremented. So if you keep the log of all the increment and decrement operations, what should be the value of the counter? So it is as simple as, the math is not so simple, but you just need to pick the set of all the increment operations that you have on the log. You take the size of it with these brackets. You take the cardinality, and then you decrement the number of decrement operations. And that is the value of the counter just by looking at the log. So this is typically what the user wants to have implemented by the data structure. So the trick about doing a CRDT is to try to do an efficient implementation of this, because storing the log all the time, well, might not be the best solution for many cases. It might be needed for cases that need some kind of accountability of what was done, but typically it's not what we want. We want a more compact way of representing the same thing. And to do it, we need to look at the specific data type we are implementing. So we can do it, for instance, for a counter. In order to see what we want, it's also good that we can resort to some kind of guiding principles that must be kept, okay, when designing this type of data types. And one of the principles is called this principle of permutation equivalence. And basically, it's a kind of a sanity rule. So if you have a data structure, like a counter that you do increments and decrements, and now I'm assigning values to the increments that I'm doing and decrements. If you look at that, you can see that even if you do the thing sequentially, you could change the operation order and you still get the same outcome, okay? So I have two traces there with different orders that lead to the same outcome, and you have guessed the result. And when that thing happens, we are constrained when doing the data type that we look at the partial order. So when we look at the partial order with the same operations, we also much reach the same outcome, okay? So that we do the same as we were expecting from a sequential execution. So this is the first principle, permutation equivalence. Now we can try to look at how can we implement, for instance, this CRDT counter from this that kind of characterizes this partially ordered execution. So in this case, we did an increment on replica B. This thing was known on replica A and B, that then increment of 35, a decrement of 5. Then you collect everything on replica B and do a further increment of 2. So how can we track this without tracking all this information? So this is not outstanding in Redis, but this is the most easy one to explain. So the idea here is to track from each replica. So it's kind of a map from each replica where you track how many increments we did in a replica and how many decrements, okay? And you keep sharing this kind of information. So now I've applied this thing into the run, and you can see that when you do an increment of 10 at replica B, you register that. You have 10 increments and 0 decrements over there. And then you ship that information to replica A. You can ship that state over there. And now, as you can see, you did a 35 increment on replica A. So you collect the two informations over there on the top section. And concurrently in the bottom part, we did a decrement on replica C, so that is also collected there. And then we can collect everything by what we call a merge operation. So actually, I'm not getting into this, but this is forming a mathematical concept called a semilattice, a joint semilattice. And that's the way we can use to prove that we are doing the things correctly, okay? So at any time, the counter value is summing all the increments and decrementing and subtracting the sum of decrements, and that's the value. So, yeah. The B is 12 because there was an extra increment on B on the run, okay? So there it is. So this is actually very glad that you asked that. So this is where we show that there is some collapsing of operations over there, okay? So we no longer have the full log where we can distinguish that we incremented 10 and then 2. We don't need that kind of information. So we collapse everything on a single one without changing the semantics of the data type, okay? So it does not grow more than that, okay, for 3 replicas. So for the concrete case of Redis, there are many different ways of implement counters. I've participated in papers with at least 4 or 5 different ways. So it's a very simple thing, and it's simply amazing that there are so many trade-offs. In Redis, there is a new different implementation. It will probably take half an hour to explain it, and it will have to be the developers to do it. So it's a different implementation that favors garbage collection. And an interesting property is that the Redis limit, and you are Redis users. I'm not so proficient with using it still. The maximum size is 64 bits, but now for Redis counters, the limit is 59 bits. So why is it so? Because there are 32 replicas, okay? And when you do things concurrently, so if you do things sequentially, you can easily check if you are overflowing, okay? But if you do the things concurrently, you might do in the 32 replicas up to your maximum capacity, but when you join everything and you want to report the value, you must still be able to be under the current API. So this is why there is a lower limit, because you can be incrementing concurrently. Now let's look at what we call registers. So this is typically what you can store on a key and assign to a key. But like more conceptually, we call this thing registers. So it's something that accepts read and write operations. And here I want to talk about something else. So if you look at the sequential execution of a register, you can see that I'm writing X, then I write J, then K, then X again. So the value is the last value. So this is what happens if I'm contacting a single instance. But we might have distributed execution on sites A and B, where actually we form a sequential execution because there was no concurrency. So in this case, there was actually no concurrency, although it could have been, okay? So we do a write X on A, and then B knows about that. It writes J, then K, and then A writes X again. So the outcome should be the same outcome as if we did everything on the same site. And there are cases that if you are not careful, you are going to ruin this expectation. And that will happen if you do if you try to implement this with what I call a naive last writer win approach. Okay, so you must be careful when using last writer win because some anomalies might appear. So now I'm attaching what we call wall clocks to this execution. So the wall clock is a local clock that you have in your machine, and you might already have noticed that there are never two clocks that are the same. So there's always a limit of synchronization between the clocks. And to make the example simpler, I'm in a case where, okay, I've started summertime savings in one of the sites, not on the other one, so we have a 1 hour difference between the sites. So what happens here is site A is 1 hour behind of site B. So you are okay writing X, and you can actually substitute it by J on site B because it is at a later time. You are okay writing the K, but then when you try to write the X value that you might remember on the site A, you have a problem. Because your wall clock timestamp is 11:30, and you want to overwrite a value that was written at 12:05. So how can you do it? You could tell me that, okay, I know that I want really to write a value, so I should accept this write and tag it with 11:30 with X. But then I will have a problem when I want to ship it to B, because by following the last writer win rules, once I ship it to B, I will not be able to substitute that value. And if I write values with a clock that is far ahead in the future, I might not be able to substitute them. And I'm contradicting what will be the sequential execution. So getting back to what a register is, so if you look at the log of operations in a register, what is the value that should be presented, giving the operations that you know? So the value that you should present is a value v that must have been written, okay? Otherwise, the register is probably empty. So v must have been written. You must find the right operation there. And then the other trick is that there is no other right operation. Actually, that should be a v prime, okay? There is no right of v prime in O such that it was written after v. So the value present, so this is your contract with the user, okay? You present a value that was written, and it was kind of the last value. So it is a value that there is no value written after it. So there's a little bug there. Sorry for that. So this is what we call the sequential semantic of the registers for the sequential execution. Now we want to see how we should work under a concurrent execution. And this brings us to the second principle, which is the preservation of the sequential semantics. So anything we do to prescribe how it should work in a concurrent setting should not contradict what happens if it happens to occur sequentially, okay? This also means that if you have a sequential execution and a distribution, you get the expected outcome. So I'm going to present one of the semantics that we have for multi-value registers. Then I will make it more concrete for Redis. So the concrete semantic for multi-value register will be able to present multiple values. Because if you look at even the sequential definition, a value should be there if it was written and not overwritten. So if you write two values concurrently, now the v prime is correct. If you write two values concurrently, you might have two values that are valid because they were written concurrently and there was no value written on the future of them because we have this partial order. So this is actually the definition of what should be the content of a multi-value register. So if we look at this execution, that case happens when we have that value y being written on replica A, and we have the right of k over there. So when we collect this information, we actually get two values. And okay, this makes some sense, or this makes a lot of sense. And to preserve the sequential semantics, you must be sure now that once you write a value in the future of those two values, it will overwrite them, and you get again a single value, okay? So this is actually what happens in the famous Dynamo paper that led to the creation of many other databases, like also Cassandra and React. They derive it from Dynamo. But for the case for the Dynamo, The actual values themselves are the contents of the shopping baskets. So when there are concurrent creation or changes to the shopping basket, the two shopping baskets can be presented, and then there is application level merge functions that will do the reconciliation between the two. I'm going to show very briefly how you could implement this, just that it's not all magic. So the way to track this is by using version vectors. So I don't think I want to spend the time explaining in detail how version vectors are. Who knows about version vectors or vector clocks? Can raise the arm? Okay. So it's not very complex. The idea is that you have one entry per site, and whenever you do something, you increment your entry. So when you write the X, you have 1, 0. And then when you write the I over there, you get to 0, and on B, you get another thing. So the good thing is that when you look at values Y and K, and you collect them together, you can compare. There are comparison rules that make sense for these vectors. You can detect that these things are concurrent, okay? So you know that you need to present the two values. And so this is how they do it in Dynamo. And you are always able to create a vector that will be in the future of 2 or 3 more vectors, as we are doing over here. So this is not the ideal way to do it. There were improvements on this. It's possible to compress the metadata, but the idea is that you need a mechanism that will show you the concurrency that happened on the system. Now I'm going to make the connection with Redis. So for Redis, there is a small use of last writer window arbitrations, but in a correct way, and I'm happy about that. So multi-value registers can allow to executions with multiple values. So what Redis does is that they actually track the causality. Suppose that it's using version vectors, as I have shown. But they also track the walk clock times that are associated with the values. And this enables to do a trick. Because since the API is the sequential API, I believe they choose not to present multiple values, although they have it internally. So they need to present a single value. So what they do is they have the multiple values, and they will present on the queries, on inspection, the value with the highest timestamp, but only among the values that are concurrent. So this is the important trick. Because if you do it, you are preserving the correctness of the sequential semantics, and you are able to present a value that had clock 1205, but still be able to overwrite it in a machine that has a clock that is in the past, okay? Because causality in this overwriting and the version vectors take precedence over looking at the walk clocks. The walk clocks are only inspected in order to deal with choosing a view from the concurrent values, so choosing the view that you are going to present in the API. So this is a safe approach. Now let's look at sets. So what is a set? Well, a set is something that you might have some content. If you add A and then add B, you expect to have both A and C. Sorry, add A and C, you expect to have both those things over there on the set, okay? And when you have adds and removes, it's also simple. So if you added C and then remove it C, you don't want to see C on the set. So this is what you expect sequentially. So in general, we can come up with this definition. So the set has all the elements that have been added, and for whose there is no remove in the future, okay? So this is what the set is. The sequential specification. Now, we can try to find, okay, now we operate under concurrency in the multi-master setting, so we need to find what is an adequate concurrency semantics for a set. So we have a case here, we have a remove and add conflict. So we are concurrently removing X and adding X on another replica. And then we need to decide what are we going to do when we collect this information. Knowing that if we add it again, the set will have to have X over there, okay? That is fixed. So the only liberty is choosing what we can do in this case. So one way to approach it is to consider that add operations are stronger, should be stronger than remove operations, and you want to see the elements over there. So that's called the add-win semantic. And you could capture that in that formula. So you want to have all the elements that have been added, and for whose elements there is no removing operation that is in the future in the partial order. Okay? So if we come back, you will see that at X, there is no remove in the future. So X must be present on the set because the remove is concurrent with it. So this is the add-win semantics. And is this familiar? Well, this is almost the same, just by changing the order relation from the total to a partial order, from what we had in the sequential specification of the set. And so it turns out that this concurrency semantic respects the partial order. For the case of Redis, the Redis CRDTs are add-win sets. So it looks that things look more or less well behaved, but there's still some important differences when we look at concurrent executions. So now, you could have thought, okay, we have all these things occurring concurrently, but can we find a way to put the operations in a sequence that respects what happened and still explain what results we have from these operations? So can we have an equivalence to a sequential execution? And now I have a counterexample that I come up with some other co-authors that will create rather strange things. So you start with X and Y in the set, and then on replica A, you add Y again, you reinforce that, and you remove X. And then actually, so you have Y over there, and on replica B, you do the other thing. So you add X, and then you remove Y. And when you collect information from the two, since it is a add-wins, and the adds were concurrent with the removes, respective removes, you want to have all that content over there. But interestingly, you cannot find any sequential explanation for this behavior, okay? Because finding the sequential explanation will force you to pick what happened concurrently and find a way to, without changing positions, find a way to put either this on front or this on front. And whatever you do, that's what I'm trying to do on that down box. If your last element is the remove X, then the X should not be there. But conversely, if the last element you choose to be the remove Y, because of the way you you order it, then the Y should not be there. So there's no way you can explain sequentially that kind of outcome. And actually, the same thing happens for the multi-value registers. There's no sequential execution that will get you into a register with more than one value, okay? So these things are different from sequential executions. They have a richer set of outcomes. And this is not the only way to make sets. So we had that option of choosing add-wins or something else, so we could have chosen something else. So this is for completeness. This is what will be a remove win semantic. So in this case, it's a little more tricky to explain, but the idea is that when you have an add and a remove, you want the element not to be over there. So as long as there is a concurrent remove, you don't want the element to be presented, okay? This is not what they do in Redis, but can be done, and someone can do a module to implement that if needed for some setting. And the way to explain that math over there is basically that you have all the elements that have been removed, that have been added, such that all the removes for that element are in the past of the add, okay? So this prohibits from having removes that are either concurrent and in the future, okay? So this is the way we capture it. Again, this is compatible with, this preserves the sequential execution, again. So with this, I've shown that once we go into a concurrent setting, things are more complicated. We have some guiding rules. We can have some choice of semantics, but this design freedom is limited by preserving the sequential executions. And actually, it could be possible to do a CRDT set where you defer this decision, add wins versus remove wins, to query time. So you could capture enough information, then it is the queries themselves that get a different parameter that will tell you if you want to show an add wins or a remove win semantic, okay? So this data type does not exist, it is a possibility. The problem is that actually remove wins requires more metadata to implement than add wins. So if you do this kind of hybrid, you will have to always pay the cost of all that metadata. So I also have an open question, is that currently the REST CRDTs, they preserve the sequential API. So maybe there could be use cases where it would be interesting to have an extended concurrency-aware API, when, for instance, for the multi-value registers, you can actually see the whole values that are stored in the system. So it's a kind of open question to the team. So now I'm going to the last data type before going to the conclusion and letting everyone go for lunch. So one of the new data types that were introduced is it's called list on Redis, but in the scientific literature, this is called sequence, and it's used for sequence editing. So you probably everyone probably used sequences in the context of Google Docs. So when we have collaborating editing on Google Docs, this is a sequence behavior. And there is an interesting paper from 2016 that defines that when implementing these things in a multi-master way, you might abide to either a weak or also a weak and a strong specification. So this is the last slide with Matt. So what is the weak specification? The thing is, if you start from an empty list, and I'm using Redis notation now because they asked me, so if you push an element there, you have element X, and then concurrently, you are putting B after X, and in a narrow application, you put A before X. So when you collect everything, what you want, what the only logical outcome is to have A, X, and B, okay? Because they are related by their relative position to the X element. So this is the weak specification, okay? And typically, all concurrent editing systems abide to this, including Google Wave. But now, let's see the strong specification. So it's the same thing, but in the middle, you remove the kind of the reference element, X. So when you collect everything, you are only going to present A and B. And you could think that, okay, since A and B were concurrent, BA could also be a likely outcome or a decent outcome. So actually, in the operation transformation-based systems and in Google Wave, the reference from the paper, probably on Google Docs, they might get you this outcome, BA. But if you want to abide to what I think is a more natural, strong specification, you should not do it. So when you place an element with respect to another element, the elements must keep the positions. So in this case, the only outcome that you are allowed to do is AB, okay? Because they preserve the order that was defined in that insertion, okay? This is very easy to implement if you can simply give it an identifier in a sequence and preserve that identifier in, within the reals from 0 to 1. So Redis list enforces the strong specification, which I think is the most interesting one. So for take-home messages, concurrent executions are needed to deal with latency. So it's not only partition tolerance and availability, it's also latency. When we have to coordinate with something that is far away, we have a problem. So if you are operating just within a data center, this is less of a problem. But in a geo-replicated setting, or in the future in the solar system, you really need to do things this way. And actually, this is the way the world operated for all our history, okay? Only now in this century that we are seeing this very fast communication. We always knew how to operate with very slow messages and local coordination. So I think that's an important thing to explore. And behavior changes when moving from sequential to concurrent execution. So some strange things happen concurrently. And in order to keep some sanity, we need some properties. One was causal consistency that I already talked about. And the other ones are the ones I just talked about. So permutation equivalence, preserving the sequential semantic, and again, knowing that concurrent executions lead to richer outcomes. And CRDTs are a tool to provide sound guidelines and encode policies. So when you are merging these concurrent executions, you know that the merge is deterministic, that the outcome will eventually be the same, irrespective of the order that the merge is done. And this is typically better than pushing it up to the application layer level. So I conclude. I'd like to thank the team here at Redis Labs, also my colleagues for feedback. And if you have any questions, I'm happy to answer them. And otherwise, we'll just go for lunch, and you can approach me outside also if you want, okay? Thank you.